This part of the higher tier science programme is about chemistry. In this section, there's more about classifying materials, changing materials, and patterns of chemical behaviour. First, more about classifying materials by their atomic structure and bonding. In the Foundation Chemistry programme, we saw how substances are made up of particles, which are either atoms, molecules or ions. We also looked at covalent bonding, when atoms bond by sharing some of the same electrons in their outer shells. And ionic bonding, when atoms bond by transferring electrons from the outer shell of one atom to that of another. For the higher tier, you need to know a bit more. Atoms, molecules or ions bond to become electronically more stable. They can arrange themselves into 4 different kinds of structures: simple molecular structures, giant ionic structures, giant covalent structures, and giant metallic structures. First, simple molecular structures. Simple molecular substances are usually non-metals and compounds of non-metals. Examples are oxygen, O2, hydrogen, H2, chlorine, Cl2, carbon dioxide, CO2, and methane, CH4. Here, the atoms within each molecule are held together strongly by covalent bonds, but the intermolecular forces between molecules are weak. Because the forces holding simple molecules together are weak, these substances are gases, liquids, or soft solids. For the same reason, simple molecular compounds also have low melting and boiling points. Because there are no free-moving electrons and no ions, simple molecular compounds cannot conduct electricity. Next, giant ionic structures. Ionic compounds are formed when metals react with non-metals. An example of this is when sodium reacts with chlorine to produce sodium chloride.
This is a chlorine atom squashed flat. With only 7 electrons in its outer shell, chlorine atoms are looking for one more electron to become stable. They're not fussy. They'll take it from any atom with an electron to spare. Sodium atoms make a natural partner because in amongst the cloud of electrons surrounding their nucleus, there's one electron sitting all on its own in the outer shell. The sodium atom is only too happy to pass that electron over to the chlorine, leaving the sodium with a positive electric charge, so it becomes a positive sodium ion. Meanwhile, the chlorine becomes a negative ion, and the scene is set for a chemical wedding. Because the bond between sodium and chlorine depends on them being ions, it's called ionic bonding. In practice, pairs of ions like this rarely exist on their own. When they gather together, they arrange themselves so positive ions are packed as closely as possible to the negative ions, and that's what gives salt crystals their regular shape.
Ionic bonds occur by the transfer of electrons from one atom to another. This creates oppositely charged ions, which are held together by the attraction between the unlike charges. The ions can pack together in a regular arrangement to form giant ionic structures. This is the atomic structure of sodium chloride, with the sodium and chlorine atoms arranged in a regular pattern. The regular pattern in which the particles of a crystal are arranged is called a lattice. Ionic compounds are usually hard substances because ionic bonds hold the ions together very firmly. The strong attraction between the ions also gives ionic compounds a high melting and boiling point. Because the electrons are not free, solid ionic compounds do not conduct electricity. Next, giant covalent structures. In covalent structures, the atoms are joined together by very strong covalent bonds. Because of this, hundreds of thousands of atoms can join together to form very large molecules, or giant covalent structures. Examples include diamonds, graphite, and polymers like polythene. This is the atomic structure of diamond. Inside diamond, each carbon atom is strongly bonded to 4 other carbon atoms. This interlocking structure of strong covalent bonds extends throughout the giant three-dimensional structure. The strong covalent bonds make diamonds very hard. These bonds require a lot of energy before they break. This gives diamond a very high melting point. Diamond doesn't conduct electricity because all the outer shell electrons are held firmly by strong covalent bonds, so there are no free electrons to flow as current. Not all giant covalent structures are hard and rigid like diamond. Graphite is made of long chains of carbon atoms, arranged in layers that can slide over each other. Polymers are long chains of hydrocarbons, which can be arranged in different ways to give different properties. There's more about polymers in the section on changing materials. Next, giant metallic structures. Atoms in a metal are in closely packed layers. Each atom is in contact with 6 other atoms in its own layer, another 3 atoms in the layer above, and another 3 in the layer below, making a total of 12. This gives metals their strength, their high density and high melting points. Metals are also ductile, flexible and malleable. They can be stretched, bent and worked.
When we stretch the piece of copper wire, you might think that we pulled the atoms farther apart. But actually this isn't what happens. In a crystal, a metal crystal, the atoms are in layers. And when we actually stretch a crystal, we slide one layer of atoms over another, like that.
The layers of atoms slide like playing cards in a pack. The way a ductile material behaves can be shown using soap bubbles. Imagine each bubble is an atom. The darting black lines show where the layers are sliding past each other. There's nothing to stop them. If this was a metal crystal, it would be changing shape in a ductile way.
So when a metal is stretched or bent, the layers of atoms slide over each other and settle neatly into new positions. The atoms in metals are also held together in a sea of moving electrons, which are free to move around throughout the whole metal structure. These free-roaming electrons also explain why metals are good conductors of electricity and heat. To summarise, metal atoms are closely packed and arranged in layers. This gives metals their high density and also makes them good conductors of heat. Metal atoms are held together with strong forces, which gives metals high melting and boiling points. Outer electrons move freely in the metal structure, making metals good conductors of electricity. The bonds between metal atoms are strong, but not rigid, which allows them to slide over each other when metals are stretched or shaped. To summarise, simple molecular structures are softer, with low melting points and boiling points, because the forces between the molecules are weak. Giant molecules are hard, with high melting and boiling points, held together by strong metallic, covalent or ionic bonds. That's the end of the higher tier section on classifying materials. In this section, there's more about changing